Cellular networks are the backbone of modern mobile communication. They are carefully planned and structured networks. These networks provide widespread coverage for mobile devices. Base stations, also known as cell towers, form the core infrastructure. Each base station serves a specific geographic area called a cell. These cells fit together like a honeycomb. This cellular structure allows for efficient frequency reuse. A central control entity manages the network. This ensures efficient resource allocation. Cellular networks operate on licensed spectrum. This dedicated frequency band reduces interference. The centralized control allows for seamless handoffs. As users move between cells, the network automatically switches their connection. This ensures uninterrupted service. Cellular networks offer high bandwidth and reliability. This makes them suitable for various applications. They support voice calls, data transfer, and multimedia streaming. Cellular technology has evolved over the years. It has progressed from early analog systems to advanced digital networks. The development of cellular networks has revolutionized communication. It enables people to connect anytime, anywhere. The widespread availability of cellular networks has transformed society. It has facilitated global communication and information access. The continuous evolution of cellular technology promises even faster speeds and greater capacity. This will empower future generations with even more connectivity. Cellular networks are a testament to human ingenuity. They connect billions of people across the globe. Several cellular network technologies have emerged over time. Each generation offers improvements in speed and capacity. Global System for Mobile Communications, or GSM, was a widely adopted second-generation standard. It enabled digital voice calls and text messaging. Code Division Multiple Access, or CDMA, was another second-generation technology. It offered improved spectral efficiency. These early standards laid the foundation for modern mobile communication. The arrival of third generation, or 3G, brought faster data speeds. This allowed for mobile internet access and multimedia services. Universal Mobile Telecommunications System, or UMTS, was a popular third-generation standard. It enabled video calling and mobile browsing. Evolution Data Optimized, or EVDO, was another third-generation technology. It offered faster data rates than earlier standards. The transition to third generation marked a significant step in mobile connectivity. Long-term evolution, or LTE, became the dominant fourth-generation standard. It provided significant improvements in data speeds and latency. LTE enabled high-definition video streaming and online gaming. LTE Advanced, or LTE, further enhanced performance. It offered even faster speeds and improved spectral efficiency. Fourth-generation LTE revolutionized mobile internet access. Fifth generation, or 5G, is the latest generation of cellular technology. It promises even faster speeds, lower latency, and greater capacity. Fifth generation is designed to support the growing demands of the Internet of Things, or IoT. It also enables new applications like augmented reality and virtual reality. Fifth generation represents the future of mobile communication. Ad hoc wireless networks differ significantly from cellular networks. They are decentralized and self-organizing. These networks do not rely on a fixed infrastructure. Nodes communicate directly with each other. They can also relay messages for other nodes. This multi-hop communication extends the network's reach. Ad hoc networks are flexible and adaptable. They can be deployed quickly and easily. There is no need for pre-existing infrastructure. This makes them suitable for emergency situations and disaster relief. Ad hoc networks are also cost-effective. They do not require the expensive infrastructure of cellular networks. This makes them attractive for various applications. Ad hoc networks operate on unlicensed spectrum. This allows for greater flexibility in deployment. However, it can also lead to interference. Nodes in an ad hoc network cooperate to maintain connectivity. They share resources and adapt to changing conditions. This distributed nature makes ad hoc networks resilient. The lack of central control poses challenges. Routing and resource management become more complex. Security is also a critical concern in ad hoc networks. The open nature of the network makes it vulnerable to attacks. Despite these challenges, ad hoc networks offer unique advantages. They provide connectivity in scenarios where traditional infrastructure is unavailable. Several types of ad hoc networks exist, each with specific characteristics. Mobile ad hoc networks, or MANETs, consist of mobile nodes. These nodes can move freely while maintaining connectivity. MANETs are suitable for vehicular networks and disaster relief. They provide communication in dynamic environments. Wireless sensor networks, or WSNs, comprise small low-power sensor nodes. These nodes collect and transmit environmental data. WSNs are used in environmental monitoring and industrial automation. They provide valuable insights into various phenomena. Wireless mesh networks, or WMNs, form a mesh-like topology. They offer greater redundancy and resilience. WMNs are used in community networking and smart city applications. They provide robust and reliable connectivity. Vehicular ad hoc networks, or VANETs, are a specific type of MANET. They focus on communication between vehicles. VANETs can improve road safety and traffic efficiency. They enable vehicles to exchange information about road conditions. Body area networks, or bands, are small, low-power networks. They connect wearable sensors and devices. Bands are used in healthcare and fitness monitoring. They provide personalized health information. Flying ad hoc networks, or FANETs, consist of unmanned aerial vehicles, or UAVs. They are used in surveillance and disaster response. FANETs offer a mobile and flexible platform for aerial communication. Section 5. Comparison of cellular and ad hoc networks. Features: cellular networks, ad hoc networks, infrastructure centralized, fixed base stations, decentralized, no fixed infrastructure control, centralized control entity, distributed control among nodes, spectrum, licensed spectrum, unlicensed spectrum coverage, wide area coverage, limited coverage, expandable through multi-hop communication, cost, high infrastructure, cost, low cost, no infrastructure required, mobility supports user mobility through handoff, supports node mobility and dynamic topology, security, relatively secure, security challenges due to open nature, scalability, highly scalable, scalability challenges due to distributed nature applications, mobile, voice and data, internet access, emergency communications, sensor networks, military applications. Section 6. MAC layer issues in wireless networks. The medium access control, or MAC layer, plays a crucial role in wireless networks. It governs access to the shared wireless medium. Collision occurs when multiple nodes transmit simultaneously. This corrupts the signals and leads to data loss. The hidden node problem arises when nodes are outside each other's transmission range. They may unknowingly transmit simultaneously, causing collisions. Fairness ensures that all nodes have equal access to the medium. Without fairness, some nodes may dominate the channel, which can starve other nodes of access. The exposed node problem occurs when a node refrains from transmitting because it mistakenly believes its transmission will interfere with another node. This reduces network throughput. Power control is essential in wireless networks. It adjusts the transmission power of nodes, minimizing interference and conserving energy. Carrier sensing mechanisms detect the presence of other transmissions, helping to avoid collisions. Request to send, clear to send, or RTS-CTS, is a handshaking mechanism that reserves the channel before transmission. This reduces the likelihood of collisions. Time division multiple access, or TDMA, divides the channel into time slots. Each node is assigned a specific time slot for transmission, preventing collisions and ensuring fairness. Frequency division. Multiple access, or FDMA, divides the channel into frequency bands. Each node is assigned a specific frequency band for transmission, which also prevents collisions. Section 7. Routing issues in wireless networks. Routing in wireless networks faces unique challenges. The dynamic topology of ad hoc networks makes routing complex. Nodes can move freely, changing the network structure. Scalability is another concern. As the network grows, routing protocols must handle increasing complexity. Security is crucial in wireless networks. Routing protocols must protect against malicious attacks. Routing protocols discover and maintain routes between nodes. They adapt to changes in the network topology. Proactive routing protocols maintain up-to-date routing tables. They are suitable for networks with stable topology. Reactive routing protocols discover routes on demand. They are more efficient in dynamic networks. Hybrid routing protocols combine the advantages of both proactive and reactive approaches. Link quality estimation assesses the reliability of wireless links. This information is used to make routing decisions. Power awareness is important in battery-powered devices. Routing protocols should minimize energy consumption. Quality of service, or QoS, routing considers the specific requirements of different applications. It ensures that applications receive the necessary resources. Location-based routing utilizes location information to make routing decisions. This can improve routing efficiency. Section 8. Routing protocols in ad hoc networks. Various routing protocols have been developed for ad hoc networks. They address the challenges of dynamic topology and limited resources. Proactive routing protocols maintain up-to-date routing tables. Optimized link state routing, or OLSR, is a proactive protocol. It uses multi-point relays to reduce control overhead. Destination sequence distance vector, or DSDV, is another proactive protocol. It maintains routing tables at each node. Reactive routing protocols discover routes on demand. Ad-hoc on-demand distance vector, or AODV, is a popular reactive protocol. It discovers routes only when needed. Dynamic source routing, or DSR, is another reactive protocol. It uses source routing to forward packets. Hybrid routing protocols combine elements of both proactive and reactive approaches. Zone routing protocol, or ZRP, is a hybrid protocol. It uses proactive routing within zones and reactive routing between zones. The temporally ordered routing algorithm, or TORA, is a distributed routing protocol. It provides multiple paths to the destination. Associativity-based routing, or ABR, utilizes the associativity between nodes to make routing decisions. Wireless Routing Protocol, or WRP, is a lightweight routing protocol. It is suitable for resource-constrained devices. The Fisheye State Routing Protocol, or FSR, is a scalable hierarchical routing protocol. It reduces control overhead in large networks. The Global Mobile Ad Hoc Network Routing Protocol, or GLOMA, uses a global topology map for routing. Section 9. Multicast routing in ad hoc networks. Multicast routing enables efficient delivery of data to a group of nodes. It avoids sending multiple unicast messages. Tree-based protocols construct a multicast tree. Data is forwarded along the branches of the tree. Core-based tree, or CBT, is a tree-based protocol. It designates a core node for the multicast group. On-demand multicast routing protocol, or ODMRP, builds a multicast tree on demand. Multicast opens shortest path first, or MOSPF, is an extension of OSPF for multicast routing. Mesh-based protocols create a mesh structure for multicast communication. Protocol-independent multicast, sparse mode, or PIM-SM, is a mesh-based protocol. It uses rendezvous points for data distribution. The Distance Vector Multicast Routing Protocol, or DVMRP, is a distance vector-based multicast protocol. It uses flooding and pruning to build the multicast tree. Multicast Source Discovery Protocol, or MSDP, is used to discover multicast sources in different domains. Protocol-independent multicast, dense mode, or PIM-DM, is another mesh-based protocol. It uses flooding and pruning to build the multicast tree. Bidirectional multicast routing, or BMR, establishes bidirectional tunnels for multicast communication. The Multicast Ad Hoc On-Demand Distance Vector, or MARV protocol, is an extension of AODV for multicast routing. Section 10. Practical applications and use cases. Cellular and ad hoc networks cater to different application scenarios. Cellular networks excel in providing wide area coverage and high bandwidth. They are ideal for mobile communication and internet access. Ad hoc networks shine in scenarios where traditional infrastructure is unavailable or impractical. They are well suited for emergency communication, disaster relief, and military operations. Cellular networks are used for voice calls, text messaging, data transfer, and multimedia streaming. They support a wide range of mobile applications. Ad hoc networks are deployed in disaster areas, remote locations, and battlefields. They provide critical communication infrastructure in challenging environments. Sensor networks rely on ad hoc communication to collect and transmit data. Environmental monitoring, industrial automation, and smart agriculture benefit from ad hoc sensor networks. Vehicular communication utilizes ad hoc networking to improve road safety and traffic efficiency. Vehicles exchange information about road conditions and potential hazards. Smart homes and smart cities leverage ad hoc networks for device connectivity and data exchange. They enable seamless integration of various smart devices. Community networking can be established using ad hoc networks. They provide internet access in areas with limited infrastructure. Military applications utilize ad hoc networks for secure and robust communication in tactical environments. Search and rescue operations benefit from ad hoc networks. They enable communication between rescue teams and victims in disaster-stricken areas. Ad hoc networks play a crucial role in connecting unconnected communities and providing communication in challenging environments.